Hello, and welcome to the outermost reaches of the solar system. I'm Adine Denton, a graduate student at Purdue University, and I'm very happy to be able to share my work with you from afar at LPSC 52. Today we'll be discussing how simulating from an impact origin, the formation of antipodal terrains to the Sputnik-Planitia Basin can be used to constrain the thermal and mechanical structure of Pluto's interior, including the likelihood of a subsurface ocean and the composition of the core. First, why is the Sputnik-Planitia Basin our best window into Pluto's subsurface? As this global snapshot of Pluto indicates, one of the most dominant geologic features on Pluto is here, the elliptical basin known as Sputnik-Planitia. Due to its large size, elliptical shape, and low topographic signature, scientists have suggested since its first observations in New Horizons data that Sputnik-Planitia is a massive impact basin. Additionally, its location and relationship to local tectonic features is one of the primary points of evidence for persistence of a subsurface ocean to the present day. Our understanding of the history of this basin and its global influence on Pluto remains an ever-evolving question, one that got a lot more interesting recently with the reveal of a new and robust analysis of Pluto's far side in fall 2019. Here, I'm showing a global mosaic of Pluto centered on the far side, meaning that Sputnik-Planitia, which was centered at 0 degrees in the previous image, is now on the edges. And what was observed upon revisiting the far side is this unusual, disrupted and lineated terrain that covers a region around 1,000 kilometers in diameter. Because this terrain is roughly antipodal to Sputnik-Planitia, it raises an interesting question of correlation and causation. Antipodal terrains are known to be produced in association with planetary scale impacts and have been observed at the Antipode 2 Caloris Basin on Mercury and Imbrium on the Moon, where they produce hilly and lineated surface features as a result of focusing of the seismic waves released from the impact point. Basically, as seismic waves expand hemispherically through the target body, they tend to be focused by planetary geometry such that they converge at the antipode. However, the magnitude and extent of the deformation that occurs at the antipode to a large impact is highly dependent on the internal structure of the target body. And because of those unique properties of large impact basins, the key questions that I will address today are, first, can the observed lineations be produced through antipodal focusing? Can Sputnik-Planitia generate the energy that's required to disrupt the surface on the scale that's actually been observed? And if that is the case, can we then use the formation of Sputnik-Planitia's antipodal terrain to constrain the internal structure of Pluto? To test that theory, I've built a small army of Plutos, each with its own varying internal structure. And I then simulate the Sputnik-Planitia forming impact into these test planets to watch what happens. Now, to adequately simulate the formation of Sputnik-Planitia, we use the ISAIL shock physics code, a hydrocode that's been adapted to handle the complex physics that are found in hypervelocity impacts. And we've initially followed a setup that was similar to that which was used in the first simulations of the basin that were done in 2016. That is, Pluto is simulated in 3 layers with a water ice shell, a liquid water ocean, and a rocky core. We extend 2 kilometers resolution to the entire body so that we can adequately resolve deformation at the antipode. And we use the inferred average impactor speed of the Kuiper belt, which is 2 kilometers per second. We did, however, have to make several significant changes. First, we had to update the impactor size in conjunction with the updated basin dimensions that were released in 2018, which almost doubled the basin size. Additionally, we use a nonlinear thermal gradient to reflect the highly temperature-dependent thermal conductivity of ice. Now, that's the model setup. But now let's get to what we actually tested. In our runs, we varied the 2 most basic unknowns in Pluto's subsurface that are likely to affect antipodal focusing: ocean thickness and core composition. We tested ocean thicknesses between no ocean at all and a 150 kilometer thick ocean, and we varied core compositions between a non-hydrated dunite core and a hydrated serpentine core. I'm now going to walk us through some of our initial results from these tests and their implications, both for the formation of antipodal terrains and for Pluto's interior. First, I'm showing you a GIF that represents a time series taken for our best fit case, which includes a 150 kilometer thick ocean and a serpentine core. In the rest of this presentation, I'll show you why that's our best fit case. But first, let's look at a few steps taken out of this time series in which material is colored according to target velocity. In these plots, the ongoing formation of Sputnik Planitia is at the top of the image and the antipode is down at the bottom. And what we're interested in is the process that's going on in the interior between these 2 points. In the first frame, we can observe the transmission of the P wave and the S wave from impact through both the core and the ice shell. But the compositional variations between them are separating the wave in the core, which is traveling faster, from the wave in the ice shell. So that as we step forward in time, the wave in the core is focused to the antipode, while it remains delayed in the ice shell, where it's isolated from the core by the liquid ocean that separates the two. It ultimately takes another 400 seconds for the wave in the ice shell to arrive at the antipode, effectively producing a second high-velocity pulse. This general trend of separation between the ice shell and the core is something that we observe in all of our runs. However, we find that the resulting deformation at the antipode is clearly influenced by both the presence of an ocean and the composition of the core, which have clearly observable effects. And it's now time for us to discuss those using strain as a proxy. The plot on the right shows strain that's experienced in the ice shell at 10 kilometers depth, measured outwards from the antipode, which is at the origin. And I'm using strain in what's called the theta-theta direction, or measured along constant lines of Pluto's longitude. This is the component with the largest magnitude in our simulations. And in our formulation of strain, positive strain indicates extension and negative indicates compression. I also have on this plot the nominal radius of the lineated terrain so that we can compare our results to it. And here we begin by plotting one of our most basic cases, which is no ocean at all and a serpentine core. So just ice over rock. And what we can observe from this initial case is that a clear zone of extensional strain is established in the region surrounding the antipode. And what I'm about to show you is that the magnitude and extent of the extension zone is dependent on the presence of an ocean and also ocean thickness. When a thin 50-kilometer thick ocean is first added, we can observe that overall strain is massively reduced. And there's a physical basis behind this reduction. It's caused by the sudden increase in impedance contrast between materials. The addition of a liquid, low-velocity layer between the core and the ice shell reduces transmission at the core ocean boundary, so more energy is reflected instead of transmitted. However, this dampening effect that the ocean has on strain and thus on resulting deformation actually starts to change as ocean thickness increases. Here is a slight increase in overall strain with a 100-kilometer thick ocean, but we're still not at pre-ocean levels. That all changes when the ocean is very thick. When we hit a 150-kilometer thick ocean, which is shown here in pink, the strain is actually massively increased. Now that might seem unusual, but it's actually because of a corollary effect that the ocean also has. So the dampening effect on energy coming through the core still holds, but that effect is actually offset by the effect of a thin ice shell overlying a thick ocean. When the ice shell is thin, like it is here, energy transmitted through the ice shell is effectively concentrated in the near surface, enhancing antipodal deformation. So thin oceans damp out strains at the antipode, but large oceans actually enhance them. Fascinating stuff. We can also note that the elevated strains in this case, the pink case, 150-kilometer thick ocean, are consistent with the estimated extent of the lineated terrain. But to explain why it's consistent, we have to come back to the other piece, which is core composition. The effect of core composition is more straightforward than that of the ocean. For a no-ocean case with dunite in white and serpentine in cyan, that is, just ice over rock, we can observe that a serpentine core produces greater deformation at the antipode. This effect is because changing the composition of the core also changes its sound speed. So a serpentine core that's lower density has a decreased sound speed relative to a dynamite core. And that decrease in core sound speed also reduces the contrast with the overlying ice shell, which results in increased energy transmission from the core to the antipode. And that's what's driving the difference in strain in this plot. And this trend, that is enhanced deformation for serpentine cores relative to dynamite cores, holds for all ocean thicknesses. Here is the same comparison for a 150-kilometer thick ocean, where the difference is even more dramatic. As such, a Pluto that has both a thick ocean and a serpentine core, which is the model plotted here in cyan, maximizes antipodal deformation by maximizing energy transmission through both the ice shell and the core, and it also maintains the correct extent of deformation from the antipode to match the estimated region of deformation that's been observed. Great, we've got something like a match. But now we need to get back to one of our original questions, which is, what kind of features would this sort of deformation actually produce at the antipode, and are those realistic? Can we tie these model results to actual geologic features? Well, the strains observed in our models are extensional, so we'd expect to get graben. And we can estimate the depth of those graben by doing a simple calculation and considering the average strain in our model to be distributed across the diameter of the terrain that's observed, and then accommodated by the formation of between 2 to 4 graben surrounding the antipode. And that number of graben that I'm using is a rough estimate that's based on looking at the lineations in the available data. And if we do that, we get graben depths of between 2 to 4 kilometers, which are similar, though slightly larger, than the massive graben that are observed on Pluto's near side, like Virgil Fossae. Since they're within a reasonable estimate, we do consider the formation of these antipodal features to be realistic, and thus suggest that they could feasibly form on Pluto from antipodal focusing. And the key point here is that we can actually reproduce the antipodal terrains, but to do it, we need both a thick ocean and a hydrated core. I'll leave you today with 3 main conclusions. First, that deformation at the antipode to Sputnik Planitia is highly responsive to Pluto's ocean thickness and the composition of its core. Second, that a thick ocean and an at least partially hydrated core are required to produce strains that are consistent with the antipodal lineations that are observed. And lastly, if we consider the implications of what that result might mean, well, with an ocean and widespread water-rock interactions like those implied by partial or complete serpentinization, Pluto might represent a much more habitable environment than previously anticipated. And so might several other large Kuiper Belt objects, which is a very fun way to think about the farther outermost reaches of our solar system. Well, thank you for stopping by, and feel free to contact me with any questions you might have about this work, or check out our paper that was recently published in Geophysical Research Letters. My contact information is below. And yes, I am looking for postdocs as I plan to graduate in spring 2022, and I would love to talk to you about Pluto, icy worlds, and giant impacts. See you at LPSC.